这个给
已解锁，请取出话筒。
防御
开始连接话筒。已解锁，请取出话筒。已上锁。
嗯 Testing. Okay. So this is a very early morning lecture. Uh, I've not been for this early for like 1 year already, maybe 2 years. Um, so I think we'll continue with content first, and then we can talk about admin stuff later when people wake up or when I wake up. Okay. So last lecture we mentioned about the Grothendieck universe, right? Set of all set. So I decided not to pursue it in class, but instead I found a reference for you. I posted out on Moodle. If you are interested, you can read it, or you can make it your project. If you decided to research more, you can write it as your project. How it settle the problem of set of all set. Basically, the definition is very interesting. So if you look down here, where's it? So they start with ZFC first, and then ZFC have this problem of set of all set. So they decided to introduce a Grothendieck universe. So basically, a Grothendieck universe has come from, well, Grothendieck, because it bears the name of Grothendieck. So they come from the seminar notes. Yeah, basically, Grothendieck organized some seminar and then they will write out the notes for it. One of the rule is it is transitive. So if X is in U, Y is in X, then Y have to be in this universe. And then if two things is in U, set of that contain that two things have to be an element in U also. And if X is in U, X power set have to be in U. Then if you have some indexing set in your U, and then there's a family of them, then you take union of them is in U. Surprisingly, this axiom you need to make it work, okay, to get a set of functions. But then there's another thing called Tarski universe. I think that one is the even larger stuff. If you're interested, you can read about those things. Okay. Yeah. You can try and make it your project if you like this topic here. Okay. All right. So this is for Gordon the universe. Any question from last lecture? Basically, last lecture, like I uploaded like about how many content? How about almost 100 pages of slide? But then most of them is those that you have seen before in like general topology class and so on. So um, for all stuff, maybe we don't want to repeat here, but then at least I will include it in the notes. But for new stuff, we definitely will go as rigorous as we like. Okay, so this applies to your presentation as well. Okay, so I have put out a schedule on the Moodle. You can try and open it up in the course info, right? So this is the thing you need to present. I'm not sure what's the length of it. You are only given like maybe 15 minutes. Yeah, we have to have some Q&A in between maybe, yeah, if we had it. So try and present it in 1 hour. We'll see how it goes. How detailed it should go. You can refer to my how I present you the set theory stuff. But your notes have to be super rigorous actually. But when you present maybe a bit sloppy, it's fine. But make sure that everyone know what I mean like how is it sloppy and then how should we feel in the sloppiness. This is the thing that we have to agree on. So I have list out a schedule here. So basically, each of you have two chances. Okay, so two times you will present. So you will present like maybe three subtopic like that. This reference here is following the Algebra chapter 0. So you can look for this later. Is it okay? Yeah, basically the one I listed down here is like the basic of groups and basic of rings and the basic of modules. So I will let you present it. And then I will continue on there. Yeah. So maybe if we follow this schedule, right? So next week will be your presentation, and then the following week will be my lecture again. And then up to fifth week we start with rings, and then you will present again, and then I will lecture again. Actually rings almost for the part that we had is covered in like Abstract Algebra 1, algebraic number theory, algebraic geometry. We already covered those. But then will depend on how you present. If I feel that your presentation is lacking some content, then I will try to add on in the next lecture also. Yeah. So it's almost like a discussion. Okay, not don't put too much pressure. I just want you to like present what you learn, what you know. Okay. Because you are master now already, right? It's not like undergrad, you just study. Now you need to try and pass on knowledge. Yeah, try to be confident with your knowledge. Okay. Yeah, because you are trying to do research and intuition in some sense. Right. Any question on this part? No? Yeah. Okay. Also, I already uploaded my extra algebra notes. Actually, those notes will cover up to, I guess, ring up. Did I put my algebra geometry notes on? Did I put on the middle? Yeah. So those will contain the ring stuff and maybe a little bit of module stuff also. Is inside that notes. Yeah. But yeah, because it because the module subtopic in algebraic geometry is like hiding in different chapters. Okay. Okay. Any problem? You can find your own reference also. Okay, but we will follow the flow in. Uh, you can find as many references as you like. Yes. This one is the labeling in chapter 0 out of the book. That's the textbook we are using. Yeah. You know what the textbook is? Uh, I already uploaded in the Moodle. Yeah, so this textbook here, chapter 0. Okay, you go and find this. Chapter 3.1, 3.2, like that. Yeah. Okay. Yeah. Okay. Okay, let's continue with categories, example of categories. Well, okay, so let's recall what the definition of categories is. Well, a category is consists of actually two data. Okay, one is objects. Second is a morphism. Well, so this morphism have to satisfy some identities, existence of identities, and then composition. You can compose morphism together. And then the composition is associative. So maybe I just put it here, associative. Okay. Right. So typically, for a category, right, you can think of it diagrammatically. So objects, you can think of it as a point, and then morphism, you can think of it as an arrow. Okay, so when you compose, it's like you are jumping around objects, something like that. Okay, every category you can draw this. Actually. So that's so good. So let's look at some special category here. So do you remember what category, like examples that we give last time? Anyone remember? What kind of category we gave last time? Any idea? Yes, category of set. Okay, so what are the morphism? Yes, function between set. Good, very good. What else? Maybe you can recall whatever you learned in undergrad. What kind of object could be category? Yes, topological spaces. Okay, the morphism are the continuous map. Okay. I'm searching my notes. Okay. And yeah, and then category of linear uh, vector spaces, category of ring, category of module, category of groups. 没卡，我在找东西。Okay, so let's look at some very kind of abstract category, but then will be useful later. So next category, yes. So suppose X is a set, and we introduce some relation, not really equivalence relation, but it has to be reflexive and transitive. Okay, it's enough. Then we can form a category. So what's this category here? So I need to tell you what's the objects and what's the morphism. So the objects here are really just the element and the elements of X. So X is a set. I just look at the element inside there. And then the morphism, what's the morphism here? Okay, so we will say that we have a morphism, let's say from A to B, as long as there's this relation between them. Okay. Okay. So maybe you can think of it. Is there an identity morphism here? Is there identity morphism here? Huh? Why? Why is there identity morphism? Because it is reflexive. Okay. Then can we compose? Compose, referring to which property? Transitive, right? So because A to B, B to C, then we can get A to C. Yeah, that's it basically. Then you need to check the identity properties. If you have A to B, B to B, is it A to B? A to A to B, is it A to B? Okay. Right, so you need to check those to be precise. Second, let's define. Okay, so some terminology here. So if the only morphism that exists are the identity morphism, then we will call these category discrete. Okay, so you can think that. So just now I told you that you think of morphism as arrow, right? So if there's only identity morphism in your category, so the arrow is like going toward yourself. So this category is kind of discrete. Then we call it discrete category. And everyone is like a standalone thing. So it's just like everyone go back to there's no arrow between objects. Okay, if, the morphism are all identity morphism. Okay, is it discrete enough? No arrow between things, right? And only every object only have morphism between itself. Okay, next, let X to be a set. So we'll define a category called X hat. Okay, so I tell you two pieces of condition here. So one is the objects. So objects here, we will consider the superset. Power set, sorry, no superset, power set. And morphism here is for every A, B in X, subset of X. Okay, because power set are subset of X, right? So the objects here are a subset of X. Or if you like, you can write it as an element of or set S. So these two represent the same thing. So I need to tell you what are their home space. So what do you think? What kind of definitions is sensible here? Huh? Yes, I guess I can just think about inclusion here. Uh, yeah, yeah. So maybe, all right, I guess. If, so if it is not a subset of one, then this home space should be empty. Hmm. Okay. Yeah. So is identity there or not? Every set is a subset of itself, right? Can you compose or not? But some this subset notation, this subset property is transitive. So now you got kind of linking like composition as transitive. Okay. Associative should be okay. Okay. Next. So third category here. So now let's start from a category. Okay. So given any category, so you have so many examples of category, right? So you can start with any of them. And let's take a single object out. Okay. Then we'll define something called the slice category. Slice category. So let's denote it as script CC. So this is a slice category of script C over C. Okay. So I need to tell you what are the objects here. Well, okay, so the objects here are actually all the morphism, okay, from something, some other objects of C to this fixed C here, okay, all the morphism. So this category, the objects here are morphism, is no longer the usual objects of the category, but it's the morphism inside the category. Okay, but with a fixed target. Fixed target. So meaning I consider all maps into the C basically. I look at all maps into this fixed objects here. So can you imagine what's the morphism here? What's the sensible things to do here? Let's say I want a map from F1 to F2. How do I define this, let's say sigma here? What do you think? Where can I put arrow, more arrows into this diagram? So let's say this is, where can I put more arrow inside? Yeah, sure. You can put C to C, but no point, right? Those are the same thing. So if I put things here, what do I mean here? Actually, I need a commutative diagram here. Okay, so I define it as a commutative diagram. Okay, that map from Z1, Z2 that satisfy this commutativity diagram. Okay. Does it make sense? Okay, so we need it to commute. Commute here means what? Do you know what it means? It just means that F1 have to be equals to F2 composed with sigma. Okay, so we look at all the sigma that make the map from Z1 to Z2 making this triangle commute. Okay. So objects are morphism, and then morphism are the morphism that make the triangle commute. Okay. A slight comment here is this is a special case of a greater category, which we call a comma category. But I'm not going to introduce now because to introduce comma category, we need functor. So maybe when we reach until functor, we will do that. But then if we follow Alufi, right, functor will come afterwards. Because functor needs some tools that we have to discuss beforehand. Yeah, the example needs some module stuff. Yeah. Maybe you can wait. Yeah. Okay. So you can imagine that this is target is C, right? So you can also similarly you can make your this target. The other one is on target. Map from where? So oh yeah, source. Yes. So now we are fixing target, right? So you can fix source as well. So then you can define something called the call slice category. So you can try and write down the whole thing, see how do you define call slice. Instead of fixing target, you can fixing source. So the triangle is like inverted. Basically, you invert every arrow, you will get the call slice category. This is a typical thing you will see in category theory. You invert things and then you get something new. Invert arrow, you get something. This is how you get homology and cohomology. Right? Okay. Next example. So we will try to make a greater diagram now. So given again a category, and now we are fixing two objects. Okay, now just previously we fixed one object. Right? Now we fix two. So we're gonna define a new category like this. Again, it's some diagram here. Okay, but this diagram here will consist of two functions. Okay, FG like that. It's like a fork, maybe like a fork. So what do you think? What kind of morphism we want to do here? What morphism we can define for this two pair of forks? What do you think? I think you should use the same logic that you think about the previous commutative triangle. Huh? Looks like diamond. So, well, I mean, like, there's two things changing here, right? So you try to put a map here, but then you try to fix your fox on as well, right? Your fox here. This is your fox one. This is the diamond you're mentioning. Well, then we require the two triangle here to commute. Does this diagram look familiar to you? In any chance? Where do you see this kind of diagram? Yeah, the direct sum or product, I think go the other way. That depends. Yeah. Okay, the direct sum stuff. Yeah. So basically, you need two triangle to commute here. So satisfying F1 equals to F2 compose sigma and G1 equals to G2 compose sigma. We have two triangles. Products are actually right projection. You can think of this as a projection. This as A cross B. You can project, and then there's a map into your products or your map out from your products. But later we will see how we get products from this kind of category. Okay, so let's keep this category here first. Well, similarly, because this target is fixed, right? You also can make your source fixed. So what do I mean by that is instead of going to AB, you can going out from AB. Okay, so the fox can go the other way. Then you will define another category. Yes. Yes. Everything here is objects in some category C. Yes. Just that we fix two of them and then we see all the maps that come from one source and then go to two of them. Okay, so far. Yeah, so maybe some exercise is a flipping arrow exercise. You can define, just now we define C subscript, right? So maybe you can define superscript AB by flipping all the arrows in C of subscript AB. Okay. Okay. Let's see. Maybe the last example before we go to next stuff. Example 5. Okay, so now we consider something called the fiber version. So fiber version. So let's call it C of alpha beta of the CAB just now. Okay. So what does it mean by a fiber version? Fiber in mathematics typically means something like the pre-image, I guess. We use fiber as pre-image. Okay. So there's something extra from the back. But in this case here, where did we put the fiber stuff? So let me write down here. So okay. So now given category C again, we don't just fix AB, we fix alpha beta, which is a map going up from A and B as well. Okay. So we don't just fix two objects, we fix the map that go out from A and B as well into the same target C. Then we define the following two things. Okay, so one is objects. Well, the objects here is very interesting. So these are the commutative diagram. Okay, so previously you will look at like random map into A and B, right? But now this alpha beta get fixed. Okay, so the fiber here you can think of the Z as a fiber part. Okay, so now we fix A, B, and alpha beta. Okay, commutative diagram. Bunch of commutative diagram. Okay, so in this case here, what's the morphism? How about I let you spend 2 minutes, draw on your iPad or what? How should this diagram, morphism looks like? Then we can try and compare. Yeah, try open up your imagination. Lucky one. 会像吧？应该，我觉得会像。啊OK OK，是。你会点一般有一般姐，看你讲话那个箭头吧。 Topologically, how about topology? Okay, so do you get this kind of picture? You get something like this? Okay, so if you want this to commute, right, I guess is enough to commute these two triangles. I think everything should commute. You just require these two to commute. I think everything will commute. This is always commuting, right? Then this outer one will commute as well. So the outer one will commute, the inner one will commute based on these two commuting. Then if we commute the inner one, I think we get everything put up nicely. Maybe it's an exercise to write it out. If you get this, so one exercise maybe I want you to do is if I get this to commute, right? Does this inner rectangle? Can I say rectangle? Not kind of square. Rectangle here commute or not? So if you go here to here, can you just go here? Okay, using the commuting table. Should we do it together? Maybe I do once so that you know what am I talking about. I'm not sure what am I saying is right, but then let's try. So my claim is alpha composed with F1 should be equals to beta composed with G2 composed with sigma. Okay, so going down this route should be the same. Okay, is it the same? Well, where should we start? Do you prefer start from left or start from right? Pick one. Left. I also prefer start from. Actually, I prefer start from right. Okay, because I want to make things easier. Okay, never mind. We start from left. Also okay. So can we build this beta G2 sigma formula? So which one can we do first? Let's think. Let me think. Huh? What? Do the F1 first, huh? Because you really have nothing to do, right? I mean, nothing more can do. So we replace F1 by, let's say it commutes there. I get F2 sigma. Right? And then, so from here you can see why associative is important now. If it's not associative, then you stop here basically. Nothing more you can do already. Okay, if it's associative, then we can see if another composition useful or not. Okay, so is another composition useful? Alpha F2. Is this useful? Is this composite useful? Because I know this commutative diagram, right? So I can replace with beta G2. Then done, basically done. Okay, so I think it's enough to just impose this two triangle, then you can make every row commute here. Okay, yeah. So similarly, you see the target here is fixed, so you can reflect, flip all the arrow and then define another kind of dual category or mirror image, mirror category. Okay, any question? Or no? So far? No? Okay. This diagrammatic category will be useful for talking about some universal property later. In particular, like those product and then direct sum stuff. Okay, next. So let's talk a bit about morphism inside category, special classes of them. A morphism F in home C A B is an isomorphism if it has two-sided inverse. So in category theory, everything is morphisms. But then morphism used differently in different subjects, right? So for example, morphism in linear algebras are linear maps. So it satisfies some linear property, right? And then group homomorphism satisfy like phi A B equals to phi A times phi B. And then ring homomorphism satisfy like preserving ring structure. Ring structure meaning you have to preserve two composite, right? Plus and multiplication. But then the isomorphism in category theory is just really something, some morphism that's invertible. That's it. Okay, invertible mean you have a two-sided inverse. Well, I mean like very straightforward property from this two-sided inverse that we first thing we prove in algebra is the inverse should be unique. And then we can denote it as a F inverse because it's unique. Only one can exist. Maybe a very quick proof to you why inverse is unique is like G equals to G times identity, right? And then we can use the other side of inverse to do this. And then we can use the associativity to make the other part identity. Oh, I think I'm wrong. So how should I make it? So I should end it with F. Let me think. So how should we keep the F? How do we prove? So maybe put a claim here. How to prove the inverse is unique? Oh, sorry. I think GF? Oh, GF? No way. Let me think. So, oh yeah, sure. G1, G2. Thank you. So suppose right, correct. Make a slight mistake. So suppose G1, G2 are inverses of F. Then G1 is equals to G1 composed identity, and then G1 is identity is like F composing G2, and then using associativity, you can write it as identity composed G2, then this is G2. Okay, so G1 equals G2. Okay. So this is just a property from this left, right. Maybe you can ask now, only using one side only. But then you can come up with counter examples. If you only have one-sided, then the inverse one will be unique. Okay. Well, so some properties you can quickly prove. Yeah, I don't want to discuss further, but you can try and prove on your own time. That is, identity is an isomorphism. Do you know why? Who is the inverse of identity map? Identity map itself. Okay. So try and check that property. Very easy to check. If F is an isomorphism, then F inverse is also an isomorphism. Why? Who is the inverse of F inverse? F. Yeah, no joke. So then from here, we can write something very intuitive. That is F inverse is F. Yeah. Okay, so the inverse of F inverse is F. Okay. Basically come from the really same equation here. It's really the same equation that you are looking at. It's just that you are looking at the inverse of this guy. Because F appear at the side of F inverse. And that inverse is unique. So F is the one that satisfies this. F inverse of inverse is F. So that's why you know that the inverse can cancel out each other. The next one I think is concerning composition. So basically, if G and F are isomorphism, then the composite is an isomorphism as well, but then I can write down the inverse. Okay, so basically this is like the matrix. inverse of matrix. Then you change the order. So why do you change the order? So you should imagine that this inverse is something that you pair out with GF, you get identity. So you should be cancelling out F first based on our composition, actually, the way that we compose. And so we need to cancel out F first and then cancel out G. So that's why F. I don't know how do you read. Do you read this come first or this one come first? Depend on how you read. I don't know. But then this F have to stick with the last F here. If you read from the right, you should say G inverse come first. Okay, but then the idea here is the opposite order because we have to cancel out F first. Yeah, some cancel G say, oh yeah, depend on the left right you put also. Yeah. Depend on the left inverse or the right inverse that you want to do. Yeah. Okay. Yeah, if you compose from the right, then you want to cancel the F first. If you compose to the left, you want to cancel the G first. So that's why this order appears. Yeah. Okay, so maybe can ask you a question. What's the isomorphism in set? Bijection? Okay, good. Okay. In topological space? Yeah, homeomorphism. Okay, good. Yeah, because you need the inverse to be continuous as well. And maybe let's look at one very interesting example here. So consider Z as a category with relation less than or equal to. Okay, so meaning if they are less than or equal to, I can put an arrow between them. It's like idea of subset. If you have a subset, then you put arrow. Okay, for example, can you give me like some arrow that works? What kind of arrow you can have here if I have less than equal to? Huh? Okay, so category is objects plus morphism, right? Okay, so consider Z as a category, meaning I take the element of Z as an object, and then relation less than or equal to, meaning I define morphism whenever there's a less than or equal to relation between these two numbers. So can you imagine what arrow I can draw here? Yeah, I can draw 1 to 2, right? Because 1 is less than or equal to 2. Okay, so this is how we like specify our categories. Yeah, subset is also like that. A subset to B, then I can draw an arrow from A to B. Yes. What do you mean? No, the morphism here is basically just telling you this relation is there. This is the arrow it wants to make. You don't think of the calculus arrow. No, it's like you should think of a morphism in category as a relation. Yeah. So arrow, yeah, arrow is important. And this arrow cannot go backward, right? Because 2 is more less than or equal to 1. Okay. You shouldn't think of it as a like a domain called domain thing. Yeah, source and target is something that you have to think about. Okay. So what are the identities? What are the isomorphism here? What do you think? That you can go forward and go backward. Just itself. Okay. So meaning the only isomorphism here are the identity. How do you prove that? How do you prove that? Yeah, this just boils down to elementary number theory. Okay, so if you want to have the two-sided inverse, at least you need to have arrow from A to B, B to A. But then this is just saying that A is equal to. So elementary number theory. Okay. Correct or not? Yeah, so if A less than equal to B, B less than equal to A, these two numbers have to be the same. And so meaning there's only one map can go between yourself. And then the only one map that you have is identity in this case. So in this case, okay, yeah, sure. Isomorphism. This is not a discrete category because you got another other. Yeah. So far, okay. Good. Yeah. Yeah. So you shouldn't think of morphism as a function. That's why I think this is a very good reason why they don't call it a function. Instead, they call it a morphism. It's like more general map. Yeah. If we talk about function, we want like an element in the domain, right? And then send to an element in the codomain. Yeah. I think this is a very good reason why they don't pick the word function, I guess. It does some similar thing as function because you got an arrow. Okay. Next, we will define something called a group point. So group point is a category in which every morphism is a isomorphism. Okay, so meaning it is kind of like a double-headed arrow. Okay, whenever you have an arrow. Okay, meaning whenever you have a map in between two things, you should be able to go backward such that they are inverses each other. Okay, so you cannot have just single arrow going to the other thing. You should be able to come back such that they compose to identity. Yeah. Okay, so every morphism is invertible. Group point. Group point. Discrete category is a group point. Discrete category is a group point, right? Wait, let me see. Is it true? Discrete category, how do you define it? The only morphism are identity, identity are invertible. So discrete category are group point. A non-trivial example. A group is a group point. A group can be a group point. You can think of a group as a single element, and then all the other group element as morphism. Because every element in the group should be invertible. So a group is a group point. Okay, you fix one group element, and then you think of all the other group element as a morphism. Oh, not fixing one element in group, but you think of the group itself as a one element. The object is the group itself. You understand? Okay, let me draw to you. So, well, like your group is that object, and then your morphism is like the G1, G2. Because you think of G is like, okay, so you should think of this G as a list of G1, G2, and blah, 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 blah. Then you multiply the multiplication table, right? You multiply by a group, then you still stay inside the group because group is closed. Yeah. So G1 times everything here, you should live inside G again. And then these are invertible. So in category sense, group is a group point with one object, which is itself, the group itself. Okay. Yeah. Other group point, I don't know already. Maybe you can find. I think group point is it one of the topics? I'm not sure. Not sure how deep can this group point go. But then I think there's a. Is there a classical definition of group point? I feel like there's a classical one, but then I don't know. You can try and find it, see if you can get the classical group point thing. Like, do you know like what is magma stuff like that? Group, semi-group, those things. I think group point is one of those things. I mean, like, yeah. Yeah, not sure. You can try and find out if there's an equivalent definition. Okay, next is automorphism. Okay, so automorphism basically is an isomorphism from A to itself. Okay, automorphism. So do you know about endomorphism? So basically, automorphism here is a subset of endomorphism. So endomorphism here basically is just map from A to itself. But then automorphism are those are invertible. Auto meaning invertible. Endo just go back to itself. Yeah, and auto is go back to itself plus. Okay, so this two term is very important because typically interesting stuff will happen in endomorphism or automorphism. And these are maybe most probably is the simplest stuff we have to look at every time. Okay. Well, you can think that here automorphism have inverse, right? And you can compose things, right? Actually, you can prove that automorphism form a group. Okay, automorphism form a group. You can try and prove it, huh? You say Gawa group is one of the automorphism group? Automorphism group. I mean, Gawa group is an automorphism between what? Between few extension? Oh, yeah, sure. Okay. But then the A here is the objects inside a category. Oh, unless you have a category of few. Okay, sure. Sure. Yeah, sure. Okay, yeah. Cool. Okay, so maybe I put a proposition here. So automorphism A is a group. Okay, right. So it's 9 o'clock. Shall we break? Any question? Or shall we go a bit further? Maybe I go a bit further because there's two more slides before we go to new stuff. So basically, so just wanted to recall the definition that we had previously, but then now we do it in a category. So a morphism, F, okay, is a monomorphism. Do you still remember the definition of monomorphism? Do you still remember? Yeah, what is it? Huh? Ah, yeah. Ah, ah, ah. Okay, sure. Yep. Mm. Cool, good. Okay, cool. Mm, 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 okay. Okay, good. Very good. So basically, we upgrade the injectivity on elements to function. Okay. Instead of we just talking about elements, we talk about function now. Okay. So F composed with alpha, F composed with alpha prime will imply that alpha equals to alpha prime. And then epimorphism will be the other way around. Okay. So maybe I skip all those notation. I let you to fill it in. So for epimorphism, you have beta composed with F, beta composed with F, beta prime composed with F, will imply that beta equals to beta. Okay, so in set theory, I think I proved to you already. Monomorphism is just injectivity, and then I ask you to do exercise yourself that surjectivity is epimorphism. So in set theory, isomorphism basically is equivalent to monomorphism and epimorphism, but there is instant that this is not true. So in particular, I want to show you before we have a break. In particular, in the category of Z that we defined just now. Okay, so we use the less than or equals to define this category here. So in this case, actually, if you think about it, every morphism there is actually both a monomorphism and epimorphism. Try and think about it. If you try and compose two things, they are the same. that should have the same map. I mean, there's no much choice you can do there. There's only one kind of error in between two things currently. Yeah, there's only one choice there. There's really only one choice in every error. Maybe. Yeah. What? What do you mean? Impossible because if you want to start somewhere here, there's only one choice here. You can take only one choice. Yeah, I mean this set is a singleton set, basically. Yeah. This set is a singleton set. I mean, like if you want to have map between one and two or one and three, there's only one map. Everything is a one map thing. Singleton set. Okay, so not much thing to check here. Okay, but then those are not the isomorphism. Okay, the only isomorphism there are identity. Just now we prove it to you. Right? Yeah, because you cannot go backward with this less than or equal to. Okay. Yeah. So in category theory, being monomorphism, being uh, epimorphism, not necessarily is an isomorphism. Okay, so it's slightly general than injectivity and surjectivity. But in set, they are the same. Okay. Yeah. Any question? So these property are easily satisfied because then we only have a single set of homomorphism set. Maybe I write it here. So the homomorphism set are singleton. If not if they are non-empty. And then the only isomorphism are the identities. Okay. Yeah. Question. Yeah, sure. Yes. Only in set is true. Maybe some other, I don't know. But in set is true, but not always true in general category. Okay. So you cannot just equate monomorphism with injectivity. But set you can, we prove it. So monomorphism and epimorphism is something more than subjectivity and objectivity. Any question? Okay, it's no question. Maybe we can have a break here. Let's break until 9:19. 什么问题？你讲哪一个 MA1 还是这个？我感觉我在这个班的 note 会3000多，不知道啊，跟 AE，我觉得会更多，我觉得会更多。天，我第一个礼拜已经100多了，我第一个礼拜已经100多了，我后面这个 Algebra 全部都没有写出来。再看呢，好了没？这没有发给我，这没有发给我，哦，你发给他的，OK，我在，他讲你们在打字，我在问他讲你打字，OK，好了，做好了，好，上一次在啊，不是做13面上次，哦是啊，跟紧啊还是还没有做跟紧啊，给其他人做，OK，hey, I think master still cannot do online attendance yet, right? Have you guys did it in different classes? No, I think no, but then no, still find your course in the system. Let me try. Oh, by the way, okay, maybe later, later we'll see how. Let's see, can I try this? Oh, I can generate sign code. You guys cannot sign to WeCom, is it? No. Have you tried? Oh, okay, okay, okay. But I can generate code for you, so you cannot sign in. Okay. And okay, so later when you present, you need to like me like what I did So in class maybe you can a little bit sloppy but then make sure your notes is like super full. Like every detail you should have proof, examples and then theorem definition. Okay, but the format don't really care So you make it your own lecture notes like that. Yeah, but need to be clear like definition, theorem, um, examples, and then proof like that. Okay. Yeah, basically I pull out these notes from my other courses. Depend on your presentation. Maybe if you like mention something extra or I think very interesting, then maybe I can put inside my notes as well. But if I think that you are lack of something that I need to tell you guys, then I will like add on myself afterwards, after your presentation in my next lecture or so. 什么东西？
为什么我们不把我们学校的 Algebra 的作品做一下？
什么叫重组？
就你看 AAY、A2 Graduate Algebra，然后 ANT、AT 这6课里面有很多次不同的东西，为什么不把它重组一下，然后把它排的更合理一点？没人思考这个问题。
对，因为我们这个，这个是其中一个，也要看学生，因为 GA 的学生不一定是从我们学校来，对对，
但是我的意思，这个我完全可以把它重组。
是，可能可以，可能可以，但是也要 depend on 那些老师怎么去想那个课。有些老师喜欢把他课想成是从头，就想过你的学生怎么
老师是从头开始，
因为我懂了，我也不知道讲 comment，我不知道啊，除非来我们有一个 algebra 的 group，然后我们可以去说哦，如果这个人要这个应该要中，但是我们没有这样的 group，没有一个是头。
其实我的意思是，比如说有的不是可以说，你可以把这几个系统筹划一下，然后再设。
可能可以哦， OK 哦。那我们老师又来来去去来来去去讲重组诶，先做出一套可以用的东西，等他们才可以去跟啊，什么讲，不然他不相信你，很难跟 PhD 讲话的。难跟 PhD 讲。诶，预判啊，can I ask you why you found SMUM? How you found it? Yeah, I know.
After I surveyed the whole Malaysia,
Oh, okay.
I found that SMUN has, in my opinion, the most promising growth analytics
Oh.
programs.
I see, I see. So how do you find us like website?
Like I searched all the universities all across Malaysia.
Yeah. How you research? I mean,
Like
website, website.
Yeah.
Oh, okay. Our website works.
I also stumbled upon your
Oh my
you
God.
uploaded a lot of videos.
I see.
And you also have a
肯定会看到。Oh, I see.
Yeah.
Okay. Okay, cool. Good. Yeah. 啊，是咩？我知道，but then 我不知道他们是看到旧的版本还是新的版本。对。Oh, okay. Good. But then, how is like pure max works in UM? Like when did you take complex analysis? Oh, you guys take year two. Quite early, but then I heard like UKM they did it like third year. Okay. Oh, okay. I think I did in Seng. Wait, when did I did it? I did it in third year actually. What easy? It can be hard, you know. Yeah.
But in our schools, teaching is easy.
Because they teach you like complex number is not complex analysis. Yeah. Complex, you guys just learn complex number. It's not complex analysis. Complex analysis is like the Cauchy integral stuff. Why do you do the residue stuff? 有啊，就后面一点点嘛，我们整个课都在学那个。是吗？Sure.
Mathematical analysis 在 real.
Okay. Yeah. Let's just bring a bit more. How about your colleagues, your friends, what they do after the degree?
I graduated early. Supposedly, my program was 8 semesters, but I completed it in 7 semesters.
How is it possible?
I took extra credit. So my friends are still in UM.
I see. Okay. 什么人？
也是弄在那里读的，
然后
用逻辑的，他讲的蛮对，
来啊，
他在想，因为他讲我是太老了，不要来了。
没有，我们中医系不是有一个50多岁？Yeah，OK 吧，应该。对吧？可是我们这边没有逻辑，我们这边没有逻辑给他读，要烟开。Hey, but UM, I thought is very famous previously. What happened to the HOD in the end? Yeah. Yeah, I know. Yeah. Then what happened to him? He left already? You also don't know. Okay, 你看的那个。Yeah. So you all know about him?
Yeah.
Oh, he told you. Okay. How is he actually?
Very nice, actually.
Teaching wise is okay lah.
Yeah. very
Okay. Maybe I can check this time. So continue. Let's continue. Okay. So let's talk about universal properties so that we can introduce very common stuff based on universal properties. Okay. So typically important things in category are two kind of objects here. Well, first object is what we call the initial objects. So what is initial objects here? Not surprisingly, most things in category we will introduce using morphism. So morphism is really a big part of category theory. So an object is initial if for every C object C there exists a unique morphism from this initial object to C. Okay, so meaning if this thing is initial, okay, everything every other element that you map into, it should be a unique element. So we call this an initial object. So if you turn it around, it will become something called a final object. I think some book call it the terminal objects, I think. Yeah, I think some books say terminal. What if we add both in? I think Alufi has some comment on terminal. What do you think? I think some books say terminal. Okay, let's include in our notes. Final and terminal is the same. So if for every object C, there exists a unique morphism A to F. Yeah. Or sometimes people use T to denote the terminal thing. What do you mean typo? I need typo. In 哪个? Oh yeah, C, sorry. Yeah. Because the book use category A, then you use A, but then we use C. Sure. Yeah. Okay. Okay, so let's see what are the terminal and initial object that we can study. Well, okay, let's give some examples based on the category that we know just now. So can you try and think of the category with the Z category with less than or equal to relation here? Any final or any initial objects here? No? So you have one objects and then you look at the map into all the objects. So can you translate this sentence into this morphism property into the category object? Can you translate it with it? So this is an object. Okay. That is morphism become what? Less than or equal to, right? Less than or equal to every other thing. Don't talk about uniqueness further. Existence first. Or existence. Yeah. Is there a number that's less than or equal to nz? No. This is exactly correspond to the well-ordering principle actually. Well-ordering principle. Z is not well-ordered. Yeah. Z is not well-ordered. So you can't even find. Don't talk about uniqueness here. Maybe it could be unique, but non-exist. Okay. If final is the same, is that one number is greater than equal to every Z. This is like the natural number is unbounded, right? Property. Okay, so no initial or final objects. Maybe I can write one of them down. I mean, write initial object property down, but then try and write down the final condition. So the initial objects in this category would be an objects, so meaning an integer, such that I less than or equals to a for all a in Z. Like that. Okay, so this is not true because of the Z is not well ordered. Okay, why no final object exercise? I'll try write it down. Okay, basically it corresponds to Z is unbounded. Yeah, so there's no number that can be greater or equal to any number. Z. Okay, how about in set? What do you think? How about in set? What are the initial objects? Any final objects? So something that map out is unique. Empty set. Okay, so empty set here is initial. So what's the unique map then? What's the unique map? So it's a function from empty set to X. So sometimes we call this an empty function actually. In the general topology, we make this thing precise because there we define function as a tuple. So here is an empty tuple actually. So there's only one way to write down the empty tuple, which is the empty set. So the function there we define as a set of tuple, and then once that set, let's say is empty, we prove that empty set is unique. So that's why we call it an empty function. So there's some definition here. Maybe you want to go back and refer to, I think I included in this note here. So this is defined as an empty relation, empty set of tuple. Any final objects? Itself. I mean, like it has to work for all objects. Do you have map into empty set? You have map into because you need to assign element in your core domain, right? I don't think you have map into empty set. Yes, singleton set. Singleton set is unique. Why? What is the way to map into a singleton set? There's only one way. Everything have to map into that thing. You cannot map into empty set. I think that violate function definition. So set. So the next non-trivial thing you should think about is singleton set. Then turns out that I think it works. So set also have final objects. For every set A, actually there is a unique map from A to the singleton set. What is that map called? I think this is the famous constant function, right? Send everything to one thing. There's really one thing you can do because once you have more things in your core domain, you can do it. But if there's only one thing, then there's only one thing you can do. So in this case, what can you see here? This singleton set is not unique actually. You can put different elements in it. But then they should be isomorphic or bijective in this set. Okay. So what we're gonna show here is without looking at any category you see, it's built into the definition of initial objects or final objects that if any of them exists, there should be unique up to a unique isomorphism. There are two uniqueness you see. There should be unique. The isomorphism you use is actually unique as well. Okay, you need up to a unique isomorphism. Okay. I cannot say they are the same set, but then they are isomorphic. in the category you consider. In set, then they are bijective. All the singleton set are bijective. Right? Yeah, you just send the singleton, the single element to the other single element. Okay, so to put it into a word, mathematical term, we'll say that if I1, I2 are both initial, then I1 isomorphic to I2. And similarly, you can write for the final version or the terminal version. Then F1 isomorphism. Furthermore, the isomorphism that you can find is also uniquely determined. Okay, you cannot pick. There's no other choices you can pick for isomorphism. Okay, so let's see why it works. I'll prove one, and then the other you will try and do exercise yourself. Yes. What do you mean? Yeah. I try to write down the precise language. Okay. Let's do one. So let's assume that I1 and I2 are initial. I1, I2, initial. See? Okay. So since I1 is initial, what is the definition of initial means? The map from I1 up to anything is unique. So in particular, a map into I2 is unique. Well, what's left to show is F is an isomorphism. Okay, so you can see uniquely determined actually come from the initial object definition. Okay, but then next you need to show that this is an isomorphism. Okay, so we have to show that it is an isomorphism. But to show something is an isomorphism, what do you need to find? The inverse. Okay, you need to find a map backward. Does there have a natural map backward? Do you have a natural map? Natural choice? All right, because I2 is an initial object. Okay, so since I2 is initial, there exists another map G, say, from I2 to I1. Okay, then what you need to check is you need to ask yourself whether GF is identity or not, whether FG is identity or not. Can you think of it? Is it Y if it's true? Follow backward thinking. If I say this is true, right, then this two have to hold. Don't need to think why this two have to hold. So you think of it like as a home space. F is going from where to where? F is going from I1 to I2, right? But then G is going from I2 to I1. So the composition is going from I1 to I1. But you need to ask yourself, what's the map from home from I1 to I1? What's this map here? What did we say about this initial objects? It has a unique map from I1 to I1, but there's a natural map from I1 to I1, which is the identity map. So if it's unique, then that's the only one. Understand? So we use uniqueness to force this identity relation. I don't care about composition. I just care about the starting point and then uniqueness. Then I have identity property already. Okay. So the natural map between I1 and I1 is identity map. And then if it is unique, then this is the only one guy inside there. Yes. Yes. And form of I2. Okay. Yeah. There's no zero map here. You don't need to worry about whether I compose to nothing. No chance for you to do that. Like maybe if you think of usual set theory stuff, right? Maybe you can compose to zero map, right? But then here I don't give you a chance to do zero map. There's no zero map between. There's only one morphism between these two, which is identity. Okay, zero map is not a choice. Because in set theory, you might think of, oh, maybe they compose to zero. But there's no chance here because there's only one map between I1 and I2. Or I2. Okay. Is it clear? Clear? 什么？
是 group 还是 ring 吧？但是 initial。
module 啊，这好像也是，ring 也是，好像 ring 嘛，对吧？ring 是，I think 我们有说过，我听我们说过 z embed 进每个 ring 里面 group 啊，group 感觉没有。I mean 我们 consider z 是 like as a ring structure 才会进到 ring 里面，but then group 的话，group 这样你只把 z 看成 group，呀，可以想一下。会有那个 why？因为你可以去加的一边，也可以去减的一边。OK，可以 start from 任意的 power。Oh yeah, sure. Okay. Yeah. Okay, right. Makes sense. Okay, good. Very good. Okay. Next, let me see. What should we do next? 1, 2, 3, 4. Okay, we're almost done. Okay. So let's any question? Any question? Okay. Okay 啊，没问题吗？问啊，什么问题？
I want because the definition say that all C with the unique morphism from I to C.
Yes. I2 is an object in C.
I2.
Correct. Yes.
But the unique morphism Y should be the one.
What do you mean unique morphism should be? So I mean like I apply initial on I1, right? So I1 to anything that's a unique morphism. What do you mean by that? Initial means, okay, let's go back to this definition. So an object's initial if for every, so you fix an object C, then you look at the map from I to C, this morphism is unique. Okay. Yeah. So I fix a object, I fix the initial object and then I fix another object. This between here, there's a unique map. Okay. So let's continue. Let tilde be an equivalence relation. Set S. Then there's a canonical projection. So let's look at x to x tilde. We will say that this is actually an initial object of the category of set. The slice or call slice. Let me see here. So yeah, if I fix x and then go out, it's slice or call slice. Huh? Call slice, huh? Yeah. I think it's call slice. Okay, so this is the call slice category. Because just now I start with mapping into a fixed target, right? Now I'm fixing the source. So this is a core slice category. But then I think we're just restricting to those functions that has the same image on the equivalence elements. Maybe some of you, if your eye is sharp, you are trying to see what am I trying to get here. Anyone can recognize? Yes, first isomorphism theorem. Okay, so let's see how this first isomorphism theorem work out. Okay, so what do I mean by this initial objects here? So we write down the definition. So basically just write down the definition. So what do we have to prove? Initial objects concerning some unique morphism, right? So there's a unique morphism. Let's call it F bar. Okay, there's a very good reason why we call it F bar later. Such that the following diagram commutes, right? So this is a triangle, I still remember about the slice category. So if you have any random map to some object F, okay, and then you have this projection here, then there should be a unique map. Okay, going from this quotient set to W. Okay, so can we define this unique map or not? How do you define this unique map? If you can recall your first isomorphism theorem, what do you do? Well, I mean, like this F bar here, right? What's the objects? I mean, what's the element? The element are the equivalent class. So how do you define map on equivalent class? You define on the representative. Okay, so you basically, well, I mean, how to define this basically is like fixed by this commutativity thing. So if you write down this commutativity, let's say I don't know what is F bar, but I know that F bar composed with pi should get F. This is what I have to know. Then basically what is this doing here is if you check on elements, this is how you define it. Then you can see that pi x is just sending s to x equivalent class. So this is how you should define it basically. If you define it this way, then this one come for free. Commutativity come for free. Then what you need to do next is to show it is well defined and then unique. And then this is basically what we did before. Okay, so maybe we can quickly mention it. Why is it unique? Because if you have other G bar, it also have to satisfy this, no matter how you define. Yeah, so this actually is the uniqueness part of it. Uniqueness comes from commutativity. Okay, so let me write down. It has to be unique. So let's settle the uniqueness first, and then we settle well-definedness. It has to be unique due to the commutativity. If you have another G bar whatsoever, it has to like satisfy the definition of fx. Then in this case, it's just F bar, X bar. Or maybe I can write more things here. Yeah. So why do we not need to check well-definedness? The problem here is with this equivalent class. Because equivalent class, you can pick different representative. So if you have a same equivalent class, you pick different representative, then this looks different. Because if x1 bar equals to x2 bar, is it clear that fx1 equals to fx2? Is that clear? So let me write those down. So hence, all we left to check is that phi bar is well defined. That is, if x1 bar equals to x2 bar, then f bar x1 bar equals to f bar x2 bar, or equivalently, fx1 equals to fx2. So, well, actually, this is how we define our f. If you notice earlier, we only restrict to those functions that have same image on equivalent class. This is why we add this line in. We only consider this kind of function. Other function might not work already. Okay. So if s1 equals to fx, if s1 bar equals to s2 bar, then meaning s1 is equivalent to x2, then we immediately have fx1 equals to fs2, because this is the only function that we care about. Okay, we don't care about random f. We only care about function that has same image on equivalent class. Otherwise, it doesn't make sense to like look at this equivalent class. Okay, like in the first lecture, we look at the decomposition of function, right? Okay. So how do we decompose a function? How do we introduce a relation there? We say that the pre-image are the same equivalent if they have the same image. Okay, so here instead of defining equivalent class using f, we have the equivalent class first, and then we look at the function that have the same image on this equivalent class. Does it make sense? Okay, yeah. So that's why I didn't say that this is an initial object of the whole co-slice category. It's just for the co-slice category that restricting to those functions has same image of this equivalent. Okay, it's not the whole co-slice category. So this is an initial object for the co-slice category that have function that has same image on this equivalent class. Does it make sense? Okay. Okay. Right. We have 4 minutes. Okay. We have 4 minutes. Maybe let's quickly run through the last two things. And then I want to make some comment. Okay. So the other thing is I wanted to say that this product of set, is what's this? This is what's this? This is unique map into it. So this is a terminal object. Okay, so this is a terminal object of this stock category that we talked about last time. Okay, product set. Okay, you can prove it, you can define it, and then this definition is actually straightforward. And very straightforward due to this commutativity. Maybe I can show you the definition of this unique map. It's basically this. Yeah. Okay. So what do you do then? This is W, right? It should be W. Am I right? Let me see. Okay, yeah, sure. Okay, so this should be the sigma you should define. So you should define what's the map going to S, what's the map going to T. As a tuple, why? Because product of set, last time we defined as a tuple or n tuple, depends on how many condition product you consider. And then you should check that this will satisfy the commutativity that. Do you know what does this projection does to this tuple? Let's say pi s on this tuple, what do you get? You just get the first term. Pi t on this tuple, you get the second term. But if you get the first term is exactly fsw, you get the second term exactly ftw. So that's why they can do. Okay, so it's the obvious thing you have to do. But then you need to check why is it unique. But then why is it unique? Again, coming from the commutativity. Because after this projection, what you left with definitely have to be distinct one. No matter how you define, it have to be equal to this. So uniqueness will always come from commutativity. You can try and write it up. I think I write it up, but then you can check. And then yeah, so yeah, this is good. And then but then there's a remark here is the terminal object of that category, right, might not be product, like the product that you think of it as a set category of set. So in this category, right, you also can try and find what is the terminal object of that category. It turns out that minimum of 2 number words there. It's not the product. What's the product in Z? Maybe you want to multiply two numbers together, but no need. Or it's just a minimum. You can try and check. This will satisfy the terminal object property just now. Okay. You try check yourself because we don't have time here. And then the other thing is how about disjoint union? We talked about disjoint union last time, right? So we union two things, but we purposely separate them out using labeling. Okay. So disjoint union would be right here. Okay. So this is going up, right? Going up is union. So meaning this is the initial. Okay, initial object of the other direction of force. So meaning this disjoint union, if you have any map out from Z, this is unique. How do you define this? What do you think? How do you define this sigma? How do you define the sigma here? I didn't define it. What do you think? You quickly think how to define the sigma. Well, I mean, to define this thing, right, you should like at least have a description of element here first. So do you have a description here yet? Okay, once you have a description here, then it should be clear that how to define this. Another thing that I want you to think about is this commutativity, right? So how does commutativity help you to write down the code? Okay, maybe we make this an exercise. Okay? I will give you answer later. I'll define one, but then the property you check yourself. So try and think about this, okay? Using the commutativity and then think about the description of element inside. Like last time I told you, right, there's a different way to talk about disjoint union, right? Depending on the label. As long as you make them disjoint, we are happy about it. Okay. Okay. So then something you can prove here is disjoint union in what's a co-product? Oh, okay. Right. So this thing is what we call a co-product in general. Okay, in general, it's called co-product. In general, it's called co-product in category. Okay, if it is initial object in this inverted form category here. Okay. In general, we call it co-product, but then in set theory, we call it disjoint union. In set category, we call it disjoint union. Okay, so this is pretty much for the universal property, but then I think after we introduce functor, maybe we can talk about limit and co-limit inside the category. Then we will see these things again in terms of limit and co-limit. Because we don't have functor language, so we cannot go into limit or co-limit yet. Once we go into limit and co-limit, we will see these things again. Okay. But for now, you just see it as a unique map into or unique map up to from that. Okay. Okay, any questions so far? Yeah, so for the exercise that I recommend you to do, right, please do because it will help you to learn or understand what I'm talking about. Yeah, please do it. For some of them, if it's not obvious, I try and write it out. It's just a similar changing arrow or what I will write it for you. Yeah. But then if you are not sure, you can send it to me. Okay, is it clear what to do? Okay. So next week will be your floor, is it? Will be your floor next week. So the first two lecture is like given by Si and Jingbo, is it? Yeah. So first 2 hours is you. And then Friday, 2 hours is who? Who? What's the name? I forgot. Did you remember your slot? Who first? 3 of you. You the last meeting you go to the week, different week. I mean next week got 4 hours, right? Ah, okay. So you are the okay. So what's the third one? Who is the third one? Aman, Pei, and Jack. Oh, you are doing the ring stuff. Okay, so you're doing group stuff. Okay, so group is doing four of you are doing groups. Huh? Okay, yeah. So you do rings. Okay. Okay. Yeah. So next week I'm free. Okay. Okay. And then another thing is I'll come up with some rubrics so that we can cross cross marking. Then I think we will get the best score for your final grades. Yeah. Best score from your friends. Yeah. And then I'll try and write down some rubrics. Okay. Yeah. Learn to be a marker as well. A lot to learn. Learn to be a lecturer. Okay. See you next week. 吓到我